Okay, now welcome to another video about probability density function of a random variable, or we call it uh, a PDF for short. So, first of all, I want to show you about exercise 1.3 and exercise 1.3 here. I won't show it, I won't prove it, but the goal that I talk about exercise 1.3 because I want to talk about the definition of Borel function. What is a Borel function? So we call function f from A to A Borel function if the inverse image f minus 1 of B of any Borel set B in A is a Borel set. It means that B here it is the subset of the Borel set of A. B here is an element of Borel set of A, and the image, the inverse image of f on B, it is also the subset of Borel. This is the definition of Borel set. So in this case, when I saw the definition of Borel set, I think about the definition of the random variable. I think the function f here, it is in the same situation as random variable because in the probability space omega fp, a random variable, let denoted by psi, it is a mapping from the sample set omega to A. And psi here is a f measurable. So f measurable and f it is a sigma algebra. So the definition of f measurable function is that psi belong to B, the set psi belong to B have to be belong to f. So this is the short form. The full form is that the set of small omega, which is the element of big omega, that satisfy psi of small omega is belong to B, and this set, this whole set is belong to A. This is the full form. And we can also write it in another form, is that psi is as measurable if the inverse image of psi in B it is belong to the sigma algebra F. So the Borel function, we can call it Borel measurable function. So Borel measurable function, I mean the difference between the function f and the function psi here is that f psi is mapped from the set omega with the sigma algebra f, and the small f here it is mapped from the set A, which is the sigma algebra is the Borel sigma algebra. It means that f is mapped like this. So what I try to tell you, what I am trying to tell you is that f and psi it is in the same situation. The difference is that the domain of psi, the sigma algebra domain of psi is any sigma algebra that generated by omega. But the sigma algebra in the domain of F, it is a sigma algebra that generated by A. So F here, it is we call a Borel measurable function or Borel function. And we will use the concept of Borel function in the next definition that I will show you. And the definition 1.7 here, it is similar to the previous. I mean, it is, how can I say, it is the same idea as the previous video about the kind of random variable that I connect the idea of random variable and the CDF of the random variable. So in definition 1.7, if there is a Borel function f psi from R to R. So that's why I talk about Borel function before I go to this definition, because we have to use it. Such that for any Borel set B, subset of R, also B it is the element of the Borel set of R. So the probability of the set psi belong to B, and this one we know from the previous video, it is equal to the CDF of the random variable psi. So can be represented as the integral over B of the Borel function f psi of h dx. So in this case, if the CDF, if the probability distribution can be represented as this integration form, so we can psi here is said to be a random variable with absolutely continuous distribution, and the the function f psi, the Borel function f psi here, we call the density of f. And the density of f, it's not just the Borel function, it also have, some property, like the first property, f here had to be, f here had to be non-negative function. Okay, non-negative function. Non-negative function. This is one. Another property is that have to be Lebesgue Lebesgue integrable function. So Lebesgue measurable integrable function, as I mentioned in the previous video. Okay, I can write it for short: integrable function. Integrable function, or f had to be belong to the space L1 of omega fp. And another condition is that the integral over the set B of f of psi of h dx had to be, integral over r is had to be equal to 1. So these are property of the Borel function f when we call it a density function of a random variable psi. And another case is that if the CDF, or the probability distribution, cannot written as this integral form, but it written as the summation form like this, so we call it psi here is said to have discrete distribution with the value, discrete value at 1, at 2, and so on. And instead of using probability density function or probability or PDF, in this case we use CDF. Instead of using PDF, we use the probability mass function that equal to this. This is the probability mass function, not the probability density function of psi anymore. So, okay, that's enough for this video. Thank you. See you in the next video.